Alright, what I want to do in this recording is give you a little preview of calculus. This material kind of precedes what you'll read in the first couple of sections in chapter 2. Calculus, you need to understand, is the mathematics of change. It involves velocities. Let's see if I can make this right. Velocities, accelerations, tangent lines, slopes, areas, volumes, just to name a few topics that we will be talking about more in detail when we get into calculus. And what you may notice about each of these things that I've mentioned is that they're all concepts that you worked with some in pre-calculus. So the question that that maybe you have in your mind is, what's different? Well, what's different is in calculus we add the concept of something called a limit. Limits are covered in chapter 2, so you're about to get into limits. But basically, if we take the limiting process and we apply it to slopes, for instance, and that's what we're going to start with, then you're going to have the calculus concept of slope. If you apply the limiting process to the concept of volume, then you're going to be dealing with the calculus concept of volume. There are two basic problems that are kind of fundamental to the study of calculus. The first of these two problems is called the tangent line problem. And to investigate the tangent line problem, I want to back up and show you, let's see if I can get into this. Hello? Maybe I need the pointer. Try that. There we go. There's the document I wanted to pull up. What you see here on your screen is the graph of y equal x squared. You'll notice up at the top of the screen in red letters, f1 of x is equal to x squared. That's the equation that I have graphed in function f1. And for those of you who are not familiar with, you're not sure what you're looking at there, I'm using some computer software called the TI Nspire teacher software. There are TI Nspire handheld calculators that can be purchased. It's certainly not a requirement for this course, but I will be using the Nspire software to demonstrate some things. So back to our problem, our tangent line problem. We have a curve, and what we want to talk about is, let's find the equation for a line tangent to the curve at point 1. So let me back up to this document. Please forgive me for flipping back and forth. And let's just pretend like that little weird thing didn't show up right there. Go away, go away, go away. Darn it. I want you to go away. There we go. Alright, so we have a curve, and maybe it's y equal x squared, maybe it's some other curve. That's not very good. Let me try again. We have a curve. Okay, now we've got a curvy curve. That's clearly not the graph of y equal x squared, so we're going to call it just y is equal to f of x. And on this curve, there is some point that we're going to refer to as point P. And what we'd like is to find the equation of the line tangent to this curve at P. So let me draw a line. Bear with me while I get this to work the way I want it to. Okay, that's not the one I want. Alright, so there's our tangent line. Alright, Well, if you're going to find the equation of a line, there are two things you have to have. You have to know some point on the line, well, point P, and we would have coordinates for point P. So we have the ordered pair for some point on the line, and the other thing you have to have is a slope. Well, to calculate a slope, you got to have 2 points. We only know point P. So here's how we get around that in the tangent line problem. We pick some other point on the curve, Q. We'll just call it Q to have something to call it. And we draw the line that goes through point P and point Q. Now bear with me while I get this to line up. And what we've got right there is what's referred to as a secant line. A secant line is going to intersect your curve in 2 places. A tangent line shares just exactly 1 point on the curve. So we've got a secant line. Now the idea is this, and if I go back to my Inspire document, I can, oh, where did it go? Uh-oh. Okay, pause. Okay, I think we're recording again. Here's my Inspire document. What I've got on this curve is the point P, that is the point that we're trying to draw a line tangent to, calculate a line tangent to, and point Q. I've also asked the program to go ahead and measure the slope of the line, the secant line PQ. Now, here's the big question. Can I make this work with all this other stuff that's going on right now? If I grab point Q, okay, point Q, oops, let me grab point Q a different way. Point Q is movable. And so what I can do, maybe, is if I grab point Q, I can slide Q closer to point P. Okay, now as I move that point, I didn't get my label attached to the point, but that's okay. As I move that point down the curve closer to point P, you'll notice that the slope of the line changes, the ordered pair for point Q changes. And what I also want you to notice is that the closer Q gets to P, the closer our secant line that does go through 2 points gets to being actually tangent to the curve at point P. Okay. So that's sort of one illustration of the limiting process. We have a slope, and in pre-calculus we know we have to have 2 points to calculate a slope. So we take our slope of our secant line, and then we apply the idea of a limit. As point Q gets closer to point P, then our secant line gets closer to actually being tangent to the curve, and so the slope we have gets closer to being the slope of the line we need. So that, kind of in a really simplified version, is the tangent line problem. The problem is we have to find an equation for a tangent line. We have to have 2 points to find slope, but we only have 1 point. The second problem that's fundamental to the study of calculus is called the area problem. And on the next page here, I've got a picture of the area problem. Okay, so we've got a graph y equal f of x, which barely fits on my screen. And what we want to do is we want to calculate the area of the region under the curve y equal f of x and above the x-axis on the interval from A to B. So we want to try to find we're trying to find the area of the region trapped between the curve and the x-axis from A to B. The problem is we don't have an area formula for a shape like this. Well, we do have an area formula for rectangles. So what we're going to do is we're going to use rectangles to approximate the area under the curve. So let's say that we split our region up into little sections. And let me grab a line tool again. Hang on just a second. We'll go with red and that. Alright. So let's say this is about halfway between A and B. So if I split that up into 2 sections and I draw a rectangle, And we've got one rectangle there, and hello, and there we go. And here's the highlighter. So here's the second rectangle. We can calculate the area of each of those rectangles, add the two areas together, and we'll get a total, which is not so great. It's not going to be a very good estimate of the area under our curve. So let me undo that. So what if instead of 2 rectangles, what if I split it up into 4 rectangles? Oops. Sorry. Bad news. Oh no! Things just went away. Okay, back up. That is about where our first rectangle was. Our first split. And let's go right there. And maybe right there. And now, when I draw in the rectangles, okay, and this is not perfect, but you'll forgive me. Now if we think about calculating the area of the 4 rectangles we've got, you can see that the area of these 4 rectangles added together, still not a great approximation for the area under the curve, but it certainly is better than the one where we only had 2 rectangles. So let's split it up into, instead of 4, let's go with 8. So I'm undoing some of the mess that I made. Alright. So I'm going to split that up. There. Oops. Missed a little bit. And there. So now when I squeeze in, okay, you'll notice that some of these rectangles stick up above the curve. Some of the rectangles are below the curve. That's okay. Now if we think about coloring in, and at this point you're very impressed at my coloring abilities, I'm sure. You think about coloring in these rectangles to represent area. We'd have 8 little areas to add together. And again, the more rectangles that we're squeezing in, the skinnier our little rectangles are, the better the approximation is when you add up the areas of all the rectangles. So if we're going to use rectangles to approximate the area under the curve, we can kind of see with at least these few examples that I've drawn badly, that the more rectangles you're able to squeeze in, the better the approximation. So the idea here is that if it were possible to smash in an infinite number of little rectangles, then the total area of the rectangles would be equal to the total area under the curve. And to be able to do that, you have to use the idea of a limit. So this is just sort of a little quick taste preview of some of the concepts that we'll be going over in significantly more detail as we move throughout the course this semester. And if I can figure out where to stop this, I will do it.